For the last few years, enterprise AI has largely functioned as a passive read and respond system of intelligence. A user enters a prompt, the system queries a static repository, and a generated response comes back. That human-scale analytics model works for generating reports or answering emails, but it requires a person at the keyboard to drive actual operational outcomes. Organizations are now moving past that read and respond model to build systems of action. In this new environment, an autonomous AI agent perceives its environment, reasons through a problem, and executes multi-step logic on behalf of the business. Generating a text summary is a low-risk operation. Noticing a localized weather event, predicting its impact on a specific transit route, and autonomously rerouting an entire physical supply chain requires absolute precision. The bottleneck in achieving that precision is not the reasoning capability of the models. It is the attempt to scale these new agents on top of legacy data stacks. Traditional architectures scatter data across separate silos. When autonomous agents try to navigate those disconnected environments, enterprise governance and access controls fracture. If the data is outdated, duplicated, or inaccessible, the agent's reasoning loop breaks down. It either fails to execute the task, or worse, it guesses, creating hallucinations with real-world operational consequences. Safely deploying autonomous agents requires an infrastructure designed specifically for machine reasoning. It requires building an AI-native reasoning engine from the ground up. Transitioning to autonomous execution requires an architectural rebuild to support machine-speed operations. Modern enterprises run on fragmented data. To analyze it, engineering teams have historically relied on extract, transform, and load, or ETL, pipelines. ETL pipelines batch data and move it from one location to another on a delay. That introduced a latency blocks an agent from perceiving the true, real-time state of the business. Manually moving massive datasets across cloud environments also duplicates the data, which increases operational costs and creates conflicting versions of the truth. The first layer is the unified zero-copy foundation, eliminating traditional ETL pipelines. A cross-cloud lakehouse architecture via the Iceberg Rust catalog connects directly to AWS, Azure, and SAP. This bidirectional federation allows AI engines to query data instantly at its source, without copying the dataset. Executing thousands of agent read and write cycles requires specific hardware acceleration to prevent system bottlenecks. The Spanner columnar engine processes complex analytical queries on live operational data by executing vectorized scans, analyzing entire batches of data simultaneously rather than row by row. Next to it, Bigtable's in-memory tier stores frequently accessed data to deliver the sub-millisecond read latency required to keep real-time agent applications running smoothly. By combining hardware acceleration with zero-copy data sharing, this foundation eliminates the latency bottleneck, providing a prerequisite for autonomous agents. Providing agents with real-time data is only the first step. There is a semantic gap between raw numbers in a database and actual machine comprehension. Large language models are built on statistical probability. If you feed massive raw SQL tables directly into an LLM's context window without explaining what the columns represent, the model is forced to guess. An agent needs enterprise-specific context. It needs to know exactly how your organization defines margin, or what physical constraints apply to your lead times. This requires the second layer, the semantic context engine, transforming flat data into a knowledge graph. Google's Knowledge Catalog aggregates metadata across the data estate, continuously analyzing and enriching it, automatically identifying how unstructured assets and structured tables relate to one another. Specialized models, like Pluto 7's PySemantic, then build a digital twin of the enterprise on top of this metadata. This twin maps the physical reality of the business. It encodes bills of materials, supplier relationships, warehouse capacities, and strict logistics rules into a format the machine understands. Isolated tables are now translated into a shared, unified logic layer. A row of inventory data is now mathematically linked to the supplier who provided it and the customer waiting to receive it. AI agents are programmed to natively query this specific graph. They do not guess relationships from raw data. They retrieve the exact corporate logic built into the system. A semantic layer grounds the agent in physical enterprise reality, ensuring that every operational decision aligns with the actual rules of the business. Allowing software to autonomously execute workflows introduces operational risk if it operates without strict protocol-level security. Traditional application layer permissions were designed for human users. They are insufficient for governing agents executing complex, multi-step actions in milliseconds. This introduces the third layer of the stack, the trust and execution protocol. When an agent initiates a workflow, the request hits the Model Context Protocol, or MCP. The protocol cross-references the request against the organization's security layer before the query ever touches the data. To maintain accountability, platforms like Pluto 7's Pi.Shield provide platform-wide observability. Every data change and AI-driven decision is logged, creating a transparent audit trail of why an action was taken. MCP governs these interactions based strictly on existing identity and access management policies and VPC service controls. Agents can only retrieve and act on the specific assets they are authorized to access. Once a query is authorized, the system requires a high-precision retrieval mechanism to pull the correct context from the massive semantic graph. This is handled by AlloyDB vector search, utilizing Google's scan indexing to scale to billions of vectors and execute retrievals at high speeds. By combining vector indexing with traditional lexical matching, the system instantly identifies the most relevant, trusted context and feeds it directly back to the agent. This embedded protocol-level governance acts as a guardrail, transforming an experimental language model into a secure enterprise worker. The zero-copy foundation provides the data. The semantic engine provides the meaning. The trust protocol provides the guardrails. Together, they function as a single, unified reasoning engine. This architecture shifts how data engineering teams operate. Instead of writing manual data pipelines and troubleshooting server loads, practitioners step into the role of orchestrators, using intent-driven engineering to direct the agents. Tools like the Google Cloud Data Agent Kit plug directly into the environments developers already use, autonomously selecting frameworks and generating code based on the engineer's intent. When applied to a live supply chain environment, the mechanics of this architecture drive immediate execution. A specialized agent, like Pluto 7's Pi agent, continuously monitors the zero-copy foundation. The moment an inventory shortage is registered in a regional warehouse, the agent perceives the anomaly. It routes the problem through the semantic logic layer to identify available inventory at nearby locations, confirms the logistics rules, clears the security protocols, and executes the stock transfer directly through an SAP integration. A human planner manually running standard SQL queries might take hours to identify the shortage and finalize the reroute. An autonomous agent identifies the problem and acts on it in seconds. Reducing the time between identifying an anomaly and executing a fix prevents the accumulation of logistics waste and avoids costly stockouts. The data platform has evolved from a static record of the past into a secure engine for real-time execution.